CBT Nuggets JNCIA series, Dynamic Routing, Vector Protocols. Well, I've been working with routers so long that back when I was working with routers, there were no switches. There was really just routers and hubs and bridges. And I've been training and teaching about routing for not quite that long, but for quite a long time. As a matter of fact, I wrote a book back in 2003 on the Cisco CCNP BSCI series, an exam cram for that. So I've been around quite a bit. And I've seen some really poor methods at teaching routing. A lot of people, a lot of instructors, a lot of trainers, what they'll do is they'll just jump right in and start comparing. Here's RIP version 2, here's OSPF, here's ISIS, here's BGP, and start comparing the protocols without actually looking at the underlying fundamentals of the differences between different routing protocols, like vector protocols versus link state protocols. And learning that kind of generic behavior or protocol independent behavior is extremely important and much more vital than just kind of learning about the different attributes of the protocol. So in this nugget, we're going to be looking at some basic fundamentals that you have to know to master before you go into the on-the-job scenario at Nugget Lab and beyond. So first thing, what's your vector, Victor? We're going to talk about vector protocols and what's going on there. And by the way, they're still in use quite a bit. We'll talk about protocol convergence with specifically distance vector protocols. We'll look at the characteristics, and of course our main distance vector protocol is RIP version 2. We'll look at loop prevention methods, and we'll also compare distance vector to path vector. What is our primary path vector protocol? Well, it's Border Gateway Protocol, BGP. Are you ready? Let's jump in. Now, in the previous nugget, we learned how to create static routes to the loopback address or the identifying address of neighbor routers in our topology. We used those static routes for our internal routers. We also created a static route known as a default route to our service provider. Those are two great reasons to use static routes. But remember, before any static routing or dynamic routing, which we'll look at here, is configured on your Juniper router, it only knows about its directly connected networks. But those directly connected networks that show up on the RIB or the routing table are extremely important. They're of prime importance for routing decisions. Because remember, static routes and dynamic routes wouldn't be able to exist in the routing table without a router's own directly connected network information. So the router can't send packets out of an interface if that interface is not enabled with an IP address and a subnet mask, or in our case, an IP address and a CIDR prefix. And it's the same way where your PC can't send IP packets out of its Ethernet interface if that interface isn't configured with the IP address and subnet mask. So let's not forget about the importance of connected routes and static routes. However, we want to look now at the advantages of dynamic routing. One of the great things about dynamic routing protocols is that they really remove a lot of our responsibility as administrators, especially in larger and growing networks, by automatically generating a routing information base, otherwise known as a routing table. And that automatic generation of information that goes into that routing table can help us to quickly find out about our network topology. Also, dynamic routing protocols have methodologies to dynamically modify or adjust to changes in traffic patterns as well as topology in our environment. It also allows for us to have multiple paths that we can do load balancing across. That's a major advantage, remember, of routing over switching. With switching, we don't want to have redundant paths, right? We have spanning tree protocol that kind of removes those for us. But with dynamic routing, we definitely want to accommodate for those multiple paths that we can use if there's, for example, an overload on one of our routers or one of our routers is down. Just like we would redirect traffic in my example showing you my different paths getting from my home to my office. Remember that? Also, dynamic routing protocols automatically at particular intervals exchange routing updates and hellos or keep alive messages to make sure that their neighbors are still there and functioning. And if there is a new neighbor or a new network, we can automatically discover that information and we can pass that information on to our neighbors or all of the particular routers in our domain or area. Another factor that makes dynamic routing so excellent is the fact that it's less prone to user error. When you're configuring static routes, you can make changes. You can make configuration errors, and if you have a lot of routers and you're doing a lot of static routing, it's more prone to user errors. Also, manually or statically configuring routes is not scalable. If you're dealing with dozens or hundreds or even up to thousands of routers, you simply have to use a dynamic routing protocol. Now, there's one other thing I want to mention here, and that is the difference between a routed protocol and a routing protocol. Okay, the routed protocol is any network protocol that offers up information in the network layer to allow a packet to be forwarded from one host to another host. So an example of a routed protocol would be the IP protocol, IP version 4, IP version 6. A routing protocol is basically the one that does the routing, or it's the one that's involved in next hop routing. And those routing protocols are the ones that we're going to focus on from here on out. And by the way, they can be interior gateway protocols or exterior gateway protocols. The three primary interior gateway protocols, or inside of a domain or inside of an area, are going to be OSPF, which is really the king, ISIS, and RIP, specifically RIP version 2. The only EGP, or exterior gateway protocol, that we're really concerned about or concerned with is BGP, Border Gateway Protocol. And that brings us to our other kind of fork in the road, right? We've got, interior versus exterior. We've got routed versus routing. But the next is basically the two main categories of protocols. That would be vector protocols and link state protocols. Let's talk about vector protocols first. By the way, I almost forgot to tell you this. Regardless of whether we're using a vector protocol or a link state protocol, the purpose or the goals are still the same. We want to discover networks, and specifically remote networks, okay? We know our directly connected networks. That's pretty much the easy part. But we want to find out about remote networks and then update our internal RIB, or routing table, accordingly. We also want to maintain or store accurate, timely routing information. If there's a change to the network, we want to be automatically updated, either on a periodic basis or through some type of triggered update whenever there's a change. We also want to find the best path or paths to destination networks. We want to discover those networks and find the best path, the cheapest, the lowest cost path, either in the number of hops or based on the link speed. And then, if a current path is no longer available, can we find new paths to our destination? So, if the current path is not available or it isn't the best path, we want our routing protocol to choose a new best path for us. And like I said, we can use a vector method or we can use a link state method. Let's learn about vector protocols now, specifically a distance vector protocol, one that you're probably familiar with, one that's been around for a long time and is still ubiquitous, RIP version 2. Now, when we get on the job at Nugget Lab, we'll need to be really familiar with two different protocols, RIP version 2 and OSPF, right out of the box. As we progress in our career, we'll start to learn more about other protocols like BGP and ISIS or ISIS. But before we can run the 60-yard dash, we have to walk first. So let's talk about vectors. Okay, vectors, you hear the phrase distance vector. What is a vector? Well, mathematically or scientifically, a vector is a quantity that has two things. It has one, magnitude, and second, it has direction. So an IP route could be a vector. What do I mean? Well, the magnitude is some outbound interface, or it could be a next hop address. That's our magnitude. And how our route's magnitude is really what kind of separates things like RIP version 2 from OSPF and EIGRP. With RIP, it's going to be router hops. With BGP, it's going to be autonomous system hops. Or it might be the sum of interface metrics that we use in OSPF and ISIS. One way to kind of think about this vector thing is to look at how a pathogen can be propagated by a mosquito. Here's what I mean. Using this analogy, the mosquito is the vector. it is the bearer or the carrier, okay? And say it carries malaria from one horse to the other horse. So mosquito A here picks up the malaria virus from horse number A and it deposits it at horse number B. Then mosquito B picks up the virus and deposits it over here at horse number C. And this concept that's used in virology is very close to what we do with a vector protocol. For example, update message A picks up the route data from here and moves it here. It now picks up the route data from here and moves it to here. Now, if you think about this, if we look at our mosquito here, the virus that our mosquito takes away from a particular horse or an organism will not be the same virus that's deposited with a different horse. The virus could multiply, it could mutate, it's going to be different. And so the same thing with the routing information. The route data that our update message picks up from a router will not be the same route data that the update message deposits in a different router. And this is how vector protocols communicate destination addresses along with their associated router data. And it's what they use to calculate the shortest path to the destination address. So let's go back to routers here. Now we know that information for a particular destination prefix has to originate somewhere. So let's say it originates over here on router A. Well, there's really three ways this router can learn the information. I think we understand these three ways. The first way is that the destination prefix is actually associated with one of the router's attached interfaces, right? That makes sense. Or the router is manually configured to originate the destination prefix. Or thirdly, the router learns that destination prefix from another routing protocol. For example, this RIP version 2 router learns it from OSPF. Now, vector protocols transmit this destination prefix information to its directly connected neighbors. And every neighbor, when it receives that route information, it'll change the information in such a way that the route information indicates the distance from that router, router B, to the originating router. For example, 1 hop. And that's what RIP does. It increases the router hop by 1. Every router that processes the information is going to increase that hop by 1. And that modified routing information then gets added to that router's routing table. Now, here's some attributes, some common attributes of vector protocols, okay? Every router in the path, let's say the path is from A to D, every router in the path is going to have a role in the route calculation. Also, a router can't update its neighbor, okay? Let's say A cannot update router B about a route until it's completed its own route calculations. It's locally converged on itself. Then it can actually update its neighbor. Also, if a destination isn't directly connected, then all a router can know about the destination is what its directly connected neighbors tell it. Okay? Does that make sense? Let me restate that. Let's say the destination is not directly connected to B. Okay? Then all router B can know about that destination prefix is what its directly connected neighbor A and directly connected neighbor C tell it. Okay? It's routing by rumor. And by their nature, distance vector protocols are susceptible to routing loops, and they're also slow to converge. And the best way to describe this is just kind of explain it in an example. Okay, so here's 3 routers. We're going to make this simple with 3 routers. Notice a couple of other things. These routers have a combination, some of them, of fast Ethernet or Ethernet interfaces and serial interfaces. And so one of the things that's unique about this distance vector protocol is the RIP protocol, like RIP version 2, it couldn't care less about the speed of the links. All it really cares about is hop count. That's its metric. So even though I might have a serial interface here or a fast Ethernet interface here, it doesn't matter. It doesn't go into the calculation. Now what we're going to have in the outset in our routing tables are just the directly connected neighbor interface information. So for example, on router A, you can see it knows about network 10.1.0.0, and it's on E0, and it's 0 hops away. It's directly connected. It also knows about 10.2.0.0 on serial 0. It's also got a metric or a hop count of 0. It's directly connected. You can see router B. It knows about 10.2 and 10.3, right? On its two serial interfaces, also 0, and of course router C over here. Now, after the first update period, we can see that router A now knows about route 10.3 or prefix 10.3. It learned it on serial 0, and it knows that it's actually one hop away. Look at router B. It now knows about network 10.4 over here, and it learned it on serial 1, and it knows that it's one hop away. And router C here knows about 10.2, this network. It learned it on serial 01, and it's one hop away. After the next update interval, you can see that router A now knows about 10.4. It learned it on serial 0 from its directly connected neighbor, and that this network is 2 hops away. Router B knows about 10.1 now. It learned it on serial 0 from its directly connected neighbor, and it's 1 hop away. And router C knows about 10.1, learned it on serial 0 from its neighbor, and it's 2 hops away. You can now say that our network is fully converged. Now, because of the way we converge our information here, distance vector protocols are highly susceptible to routing loops. Every router only knows its directly connected link and what its neighbor tells it. And poor information can be propagated very easily, and it can mess up your network. It's kind of like that game you played as a kid where 10 people sat down in a circle, and the first person whispered into the ear of the person next to him and said, "Billy eats spaghetti with a knife and a spoon." And by the time it gets back to you, it's, "Will he be ready to fly a kite in June?" That kind of thing. So because of the routing loops, distance vector protocols have lots of mechanisms in place to help countermeasure and solve some of these problems. Let's talk about some of those mechanisms. Okay, at this point you might be asking yourself a couple of questions. Number one, why are distance vector protocols more susceptible to routing loops? And number two, you might be asking this question: what does it matter? Okay, you might be thinking, we're 20 minutes into this particular nugget, and I want to get to the configuration. I want to start doing configuration of RIP version 2. I want to start configuring OSPF so I know how to do this when I get to Nugget Lab. Well, let me tell you something. There is a one-word answer to why this is so important, and the answer is troubleshooting. Okay, when I got my first car, it was a Firebird back in the day. And I did more with that vehicle than just learn how to shift it, because it was definitely a manual transmission. Shift it, put gas in it, look at the speedometer, steer it, all those basic things. I figured out how to get under the hood, how to change the oil, how to change spark plugs, how to do a tune-up. I mean, I learned under the hood stuff so I could fix problems, because I was a cheap teenager without a lot of money. Well, here's the deal. When you walk into Nugget Lab, it's not going to be enough to be able to go to your Junos routers and configure OSPF and RIP version 2 and ISIS and BGP, because the bottom line is, fundamentally, it's not that hard. What's difficult is troubleshooting. And if you don't understand the behavior of distance vector protocols versus link state protocols and path vector protocols, then you won't be able to effectively troubleshoot. You won't be able to effectively design your network properly. So, getting back to the task at hand, we need to understand why distance vector protocols have routing loops and slow convergence. Here's why. Because they only know what their directed connected neighbors tell them. Okay, router A over here only knows what directly connected router B tells it. It doesn't have a picture. It doesn't have a mathematical algorithmic picture of the entire network topology or the entire network domain or area. So, distance vector protocols have to have different tactics, different mechanisms for handling loops and other convergence problems in their networks. For example, this topology was an excellent way to kind of understand how distance vector protocols share routing information, but very few networks look like this. Okay, one single path through a bunch of linear routers through your campus network. Okay, usually you're going to have redundant paths, multiple links from the access layer to the distribution or the collapsed core, and redundancy throughout, even going out to the internet. And in an ISP network, a service provider, they're obviously going to have many paths, maybe only 7 routers deep at the most, but they'll have lots of options as far as the breadth of that network. Router D actually has information about a upstream destination route at 10.1.1.0/24. It knows about that. What it shouldn't do is it shouldn't send an update back upstream to router C. At this point, router C will think it's got another way to get to 10.1.1.0. It can get there through router B. It can also get there through router D. Now, we have mechanisms in a stable network to deal with that, but suppose the real route to 10.1.1.0 is suddenly invalid. Okay? Well, router C is going to install an entry in its routing table saying, look, to get to 10.1.1, that's 4 hops away going towards router D. Well, if a packet with a destination of 10.1.1.0 is forwarded to router D, it's going to go right back and forth between router D and router C. It'll just ping pong between them until the TTL expires, right? Well, that's fine if it's just one single atomic packet, but most communications are a bunch of packets. So we've got a bunch of packets ping-ponging back and forth between C and D. That's not a good thing. So what we have is a rule called split horizon. That's one of the mechanisms that we use, one of the anti-loop mechanisms in a distance vector network. Split horizon says that an update for a destination can't be sent to the neighbor from which the destination was learned. In other words, updates must never be sent upstream, only downstream. So D learned about network 10.1.1.0 from its upstream neighbor, router C. Therefore, it will never send an update back upstream. But what about this network? Routers B, C, and D have a physical loop here, which is a good thing because that adds some redundancy, but loops are a problem for vector protocols. Now, when router A advertises the 10.1.1 network, it advertises it downstream to its only neighbor, router B. But then B is going to advertise that subnet 10.1.1.0 to its neighbors C and D, which are also downstream from it and from router A. But router C and D are where things become kind of weird. Router D sends an update to router C saying, hey, I know about network 10.1.1 and it's 1, 2, 3 hops away. And of course, router C is going to update router D going, hey, I know about network 10.1.1.0. It's 1, 2, 3 hops away. Now, the reality sits in that in most situations, the split horizon rule that we talked about will take care of those ambiguities. But remember, router C and router D, before they sent those updates, they already have entries in their own routing tables that say that network 10.1.1.0 is 2 hops away, right? 1, 2. So when router C receives router D's update and router D receives router C's update and it notices that the hop count is longer, or 3, a longer distance than what it already has in its routing table, well, it's going to drop that update. Now, what happens, let's say, if this link gets broken? And this is where our redundancy is a good thing. Router C knows from its link layer 2 protocol that the link has failed to router B. And so the next hop router B to network 10.1.1 is no longer usable. So C can then choose the next best route to 10.1.1, that's via router D, 3 hops away. Now, how does router C learn about this information, this next hop route? Well, it depends upon the vector protocol. RIP and RIP version 2 are going to send periodic, unsolicited updates to their neighbors. If these were BGP routers, which is also a vector protocol, well, each one of these routers will be storing alternate routes in a table. So let's say the network link between B and A goes down, and before B can send an update of this change to C, D has already sent an update to C, which C thinks is the most accurate information, but it's not. B has the most accurate information. And so there can be timing issues. There's these windows because of the slow convergence of distance vector protocols. Specifically, there's these time windows where bad information can be propagated. Well, because of that, there's a count to infinity mechanism that's in play here, because this circular logic of updates could just go on and on through infinity. And what counting to infinity is going to do, it's going to make this link to A kind of perpetually down, even though it's not. So what RIP will do, RIP version 2, is it has a maximum of 16 hops. So the first router that increments the route to 16, it will mark it as unreachable. Then it updates its downstream neighbor that the route is unreachable. This will eventually stop that counting to infinity loop. Now our real solution for preventing this counting to infinity problem is what we call a hold down timer. And this should be familiar, okay? Remember when we were looking at the routing tables earlier and we saw up there in parentheses the number of routes, and one of them was saying how many routes are in hold down, okay? Well, that was exactly what our routing table was trying to tell us. If any of those routes were in a hold down state because these hold down timers have kicked in. Now, the problem with hold down timers, well, let me say the good thing about hold down timers is that they prevent this count to infinity problem, right? Because if a router learns a route from a neighbor and then it hears from that same neighbor that the route has become unreachable, a hold down timer is going to be set for that route. And until the timer expires, that router will not accept any new information about that destination unless it either comes from the same neighbor that announced the route was unreachable, or another neighbor advertises a route to the destination with a distance that is equal to or less. In other words, less than or equal to the distance of the original route. In other words, better information. The problem with hold down timers is that they're effective, but they have a pretty steep price. The hold down timer for RIP is 180 seconds. So they can really increase the network convergence time. In networking terms, 180 seconds is a long time. I mean, think about taking 180 seconds to download your home page through your browser. So we can see we've got these mechanisms in place to prevent loops and the counting to infinity problem, that looping situation, but all of these things with vector protocols come with a price. Now a distance vector protocol like RIP version 2 is what we refer to as an interior gateway protocol. In other words, it only carries information about routes and destinations within a particular AS or autonomous system. What about carrying information, route prefixes, between autonomous systems? Well, there we need an exterior or an external gateway protocol, and the one we're going to be learning about is BGP. Now, going to be learning about, what I mean is in the JNCIS series. In the next series after this is when we really dig into BGP. But remember, BGP is also a vector protocol. It just happens to be a path vector protocol. Even though this is a philosophical difference, it could technically be referred to as a distance vector protocol. It just doesn't use hop count, it uses paths. And so these routers here, as opposed to being RIP version 2 neighbors, they could be BGP peers, like the routers between service providers or points of presence on the internet, for example. So for example, this router right here could be in autonomous system 65,027, and these peers could be in autonomous system 65,002. And we need some type of protocol between these autonomous systems, BGP. So since BGP is a vector protocol, it can have loops as well, right? Absolutely. It actually has a really easy loop avoidance mechanism. Now, the basic measure of distance in the BGP protocol is the autonomous system hop, okay? So I'll say AS hop. Now, instead of measuring this distance as an AS hop count, it associates with each destination prefix an attribute, specifically a route attribute that's called AS underscore path. And this is really a list. It can be a sequence list, it can be unsequenced, but it's basically just a list that says these are all of the AS numbers of all of the autonomous systems that route passes through. So if you want to find the shortest path to a certain destination prefix, the router is going to choose the route to the destination that has the least AS numbers in its path. Okay? So the least hops in that sense. The least hops through autonomous systems would be the best path. And since AS numbers are globally unique, you have to go through an organization to get them, no two numbers for different autonomous systems would be the same. So when router B receives information from its peer, router A, an update, for example, from its BGP neighbor, it'll look at the AS path of each route the update contains. If the router sees its own AS number in the route's AS path, for example, B sees its own AS number in there, it knows that the route has already passed through it before. So what does it do? It's a loop. It drops it. Pretty cool. Now that's a simplified explanation of path vector, but that's basically how we avoid loops. We look at the update, we look at the AS path, and if we see our own autonomous system in there, it's already passed through here, so it's going to probably be a loop. So for the exam, that's pretty much the extent of your knowledge that you need to have for BGP, okay? It is a path vector protocol because it doesn't track paths through routers, but paths through autonomous systems. So really the difference between distance vector and path vector is kind of semantics, right? The semantics being, well, a RIP version 2 distance vector route is the sum of quantities, okay, the sum of hops, whereas path vector is a sequence of quantities, a sequence of autonomous systems. Okay, so there you go. When it comes to vector protocols, you can do more than just steer the car or put gas on the car. Now you've seen under the hood, you've seen some of that basic behavior, and now we have a fundamental knowledge that'll help us as we go further, especially in the JNCIS, and start configuring and monitoring and troubleshooting. Now we do have a RIP version 2 lab coming up a little bit later on in this nugget, and that'll really help you to have that fundamental under the hood knowledge. Again, like I said, BGP is covered in great detail in the JNCIS and beyond. Well, in this nugget on dynamic routing, specifically vector protocols, we started out, of course, looking at vectors, and we used the Mosquito as our example of a vector delivery system. Then we looked at protocol convergence, characteristics of distance vector protocols, loop prevention mechanisms like split horizon, and hold down timers, and then finally, distance versus path vector. I hope this CBT nugget has been informative for you. We'll see you in the next nugget on dynamic routing, where we look at link state protocols, specifically OSPF and ISIS.